Hello everyone. In this video, we are going to talk about the geometry of roughness and ruggedness. In this picture, we can see a rough and rugged coastline. It is very hard to measure the length of the coastline. Countries keep updating the length of the coastline. For example, India updated the length in 2025 from 7,000 to 11,000 kilometers, not because it acquired any new territory, but because of access to higher resolution satellite imagery, which could essentially map the creeks and fissures in the coastline to give a better estimate. Here we see a time series data, let's say stock market data. So, and as we zoom into a particular part of it, essentially see the replica of that part. As we keep zooming in, the replica it is just a replica of the zoomed out part. So just replicating over length scales. This is the dendritic solidification of ice. So by dendritic solidification, it is meant that due to certain disturbance in the solid liquid interface, the solid liquid interface basically grows like dendrites, meaning like trees, which the trunk branches out, and then the branches branch out into twigs, and similar thing we can see in the snowflake solidification. This is Apollonian gasket. This is one of the integral part of our topic, and basically if you have three circles and an exterior circle, so you just keep plugging circles in the space which are left out, and just keep on packing the space. So all these kind of properties, these Benoit Mandelbrot in the 1970s, he termed he coined this term fractals. Although the like people have been doing this thing from antiquity, but the term has been finally sealed by Benoit Mandelbrot, who was a mathematician working in IBM, and it is derived from this fractus called fractured and fragmented. So essentially, what do you mean by dimension? So suppose this line, we have to measure it by a segment, exactly half of it. So we need two segments of this length of this length to cover this one. Next we have a slice. We need to cover an area. We just half we want to cover the area by a slice of half the edge length, and we just need the square, like four slides of this one of half to cover the area. So dimension, essentially we have been very acquainted with dimension being an integer, so either 1D line and 2D area and so on, which is true if the boundary is smooth or differentiable. For example, we have taken a smooth curve here and exact same curve here, just the grid points have been halved, and if we count the number of boxes it passes through, we see that 1 2 3 4 5 and 6, and just half we expect it to be 12, and it turns out to be 13. So it's sometimes like 2n plus 1 or 2n minus 1 according to the endpoints we choose, but essentially it just double half the grid size, double the number of boxes. Okay, but it's not so if the curve is not smooth, if it is like a coastline, if it is rugged. So Benoit Mandelbrot, again, I mean, he wrote this article, "How Long is the Coast of Britain? Statistical Self-Similarity and Fractional Dimension." So essentially, we get that fractals have fractional dimension. We'll come to that, and because they have fractional dimension, is another reason to call it fractals. So he wrote this book, Fractals and Chaos, and this Mandelbrot set the Mandelbrot set and beyond. So Mandelbrot set is essentially generated in the complex plane with this recursive equation. But getting back to the topic, we can define dimension by this equation, where n is the number of self-similar pieces and s is the scaling factor. Naturally, if we for a perimeter, for measuring a perimeter, half the number of pieces, like half the scaling factor, and you need double the number of pieces. But not so here. uh, just beg your pardon, yeah, sorry about that. Oh yeah, coast of Britain. So uh, this Ireland is included in the map. So apologize to the Irish people. I don't intend to call you British. But the crux of the matter is that, yeah, so we divide it into half, grid size of length of side half, but it does not necessarily mean that we need double the number of boxes to cover the perimeter of the British Isles. So following here, this dimension d is simply a log relation between the number of self-similar pieces and the scaling factor. Now we have to use this limiting term simply because, well, I mean, if we can go without the limiting term if we are measuring a smooth curve, but for a rugged curve we have to essentially, uh, it is defined because it's zooming in more and more is essentially equivalent to making finer and finer grids, so the scaling factor tends to 0, and then the log relation with the number of self-similar pieces, and it's giving us the Minkowski dimension. Okay, now we have something which is a theoretical case, which which von Koch basically wrote this article on a continuous curve without tangent obtained by an elementary geometric construction. So essentially what it means is that take a line and divide it into, like, make it 4/3 of the length. So at each step the line is replaced by 4 smaller segments of length 1/3 of the original line. So essentially we just make these things after each iteration, we just replace one line segment with 4 smaller, and plug it in with yeah, one, we replace one with four smaller segments of length 1/3 of the initial line segment, and just plug it in. So if you do it on a triangle, we get what is called the Koch snowflake. So for infinite recursion, if it goes on infinitely, we can see that the length L goes to 4/3 of L, which increases by a factor more than 1. So essentially the perimeter of the Koch curve is infinite. However, the area of the Koch curve is finite. So this can be proved with some algebra. This like pretty simple algebra, we can arrive to this, that the area of the Koch curve is 1.6 times of the area of the triangle. Very interesting. So the perimeter is infinite, but it's a finite object in 2D, in area. The area is finite. It exists. Okay, so the Minkowski dimension of Koch curve can be calculated from the formula in the we have discussed seconds earlier, which is this. And because we know, I mean, this follows a recursion relation, we know that, I mean, we don't need the scale to go to infinitely less, so we can just say that the dimension is 1.26. But however, this is regular in nature. This we have artificially defined. But for the coastline, yeah, it begs box counting. Okay, so these are the simulations run on Wolfram Cloud. It just packs the packs the British Isles with fine boxes, and it packs the Japan with fine boxes, and it turns out that of a log-log plot, the slope for Britain turns out to be 1.255, and for Japan it turns out to be 1.119, which essentially says that it's a measure of ruggedness. So at least relatively we can say that the British Isles is we can safely say that the British Isles is the coastline of the British Isles is more rugged than the island of Japan. All right, so here we have Carl Wirtstrass, who gave this in a series form for the first time. He gave a function that is differentiable nowhere and is self-replicating and continuous. So yeah, just we can run this video. Yeah, really? All right, maybe something wrong, but oops. Yeah, no, yeah, okay, oops. Yeah, so essentially, if you see, if you pause at A.25 and B4, then yeah, the definition is A lies between 0 and 1, B is greater than 0, and it starts appearing when AB is greater than 1. So here AB is exactly, the product AB is exactly 1, and from here, yes, sorry about that. Oops, again, yeah. It has started to accumulate more and more. Yes, pretty much. Alright, so just returning to the initial, oops, yeah. So for n equal to 0, hmm, and a equal to 0, it says it's a pure cosine curve. Okay, so a starts from 0.01, so that means a was 0, and when a is 0, yeah, all the terms are 0 except for n equal to 0, which means 0 to the power 0, okay, it gives 1. Something raised to the power 0 is always 1, and 0 when raised to the power something, 0 when raised to the power something is 0, and something when raised to the power 0 is 1. Oops. Okay, so you have worked this out. Take this limit, and it says it's 1, but it's still very controversial. You can read Donald Nutt's has written an article on this. Alright, yeah. Okay, so it's just a zoomed in picture, and here we have essentially proved that each term is bounded because cosine lies between the absolute value of cosine lies between 0 and 1. So this is essentially bounded. So fx is bounded at 1 by 1 minus a, and here we can see that absolute value is 2. So we can safely say that a is zero point 0.5 here. So what it says is that if it's a smooth curve, there exists a tangent, and this is just high school calculus. So it's not differentiable at sharp point, and essentially all points are sharp points. So none, it's differentiable nowhere. Oops, really? I don't know. Planck length, extremely mysterious. Okay, so now we come to our target topic, the Apollonian gasket. It's a space filling iteratively, and it takes us to antiquity. Apollonius, the Greek mathematician, he belonged from this city, Perga. Yeah, it's it's present day Turkey. So his question was, construct circles that are tangent to three given circles on a plane. Very simple. Just construct a circle which is tangent to three given circles on a plane. And slowly the problem has evolved, and we need to pack it up with even more tangent circles, so on. So Rene Descartes was the first was sorry about that. Rene Descartes, I always get excited when I speak about Descartes. So Descartes had correspondence with the Princess Elizabeth of Bohemia, and Bohemia is present day Czech Republic most likely, and he offered a solution in his letter in 1643. And then Leibniz, who was born around this time 1646, then he took up this topic, and finally Edward Kästner in the 20th century, he named it Apollonian Gasket. So the name goes after, I mean, the credit of the name goes to Edward Kästner. All right. So the solution of Descartes, pretty much boring, but not so boring. So this is high school trigonometry identity. It can be found in books like S.L. Loney, and these are the angles alpha, beta, and gamma. And this is one, we need one identity, and we need to apply the cosine law of triangles to each of the three triangles, and we find these relations cos gamma, cos beta, and cos alpha, and we just place these values in the initial identity, and doing some middle school algebraic manipulations, we find out that that the that the that the square of the sum of the curvatures, okay, so radius, so curvatures are just inverses of radius, so the square of the sum of curvatures is equal to twice the sum of the squares of the curvatures. That's it. Okay, then we see Now that we know four, like we get 4, 1, 1, 2, 3, and 4 circles mutually tangent. Now our task is to generate space filling circles. Pretty simple. We start with our relation that we derived, and essentially we treat it like a quadratic in K4, and then by simple middle school algebra, sum of roots of quadratic. So K4, so this has two roots. One is this externally tangent. So this circle is tangent to C2, C1 and C3. This is also tangent to C1, C2 and C3. So because we know this one in our first iteration, already we know it. So therefore we can get the next circle like this. So just iteratively we can apply this rule and generate curvatures of the circles, space filling circles accordingly. Frederick Soddy wrote this. I don't know why. I mean, he was an experimental chemist. Won the Nobel Prize. Here's the link of his Nobel Prize lecture. And he worked along with Ernst, Ernst Rutherford. And his topic was radioactive isotopes. So on radioactive decay, alpha decay, beta decay, and so on for uranium and thorium series. So he made this problem very famous in calling it the kissing circles problem, and he wrote this article in Nature in 1936. He wrote this poem, basically, I should say, very very mathematical, or is it very very romantic. So he generalized for 3D and for ND. Essentially, in 3D you will have 5 kissing spheres at most, and for n dimension just an extension of this in n plus 2 sorry about that. In n dimensions there are n plus 2 hyperspheres possible. All right. So we'll see what happens if we put integers. If we have the initial 4 circles as integers, that is to say the interior 3 circles, curvature is shown here 2, 2, 3, and just another the external circle has curvature of -1, because of course it is internally tangent and not externally. So we see that if the initial 4 circles, like the curvatures, are integers, all the next circle generated have integer curvatures, which is very interesting. But from what we have derived, like 15, okay, so twice of k1 plus twice of k2 plus twice of k3, that gives, okay, that gives 14, and minus k4, so this is minus of -1, so that gives 15. So couple of slides earlier we have done that. So essentially we can find out that okay, so that's done. Initial 4 circles integers, next all will be integers. And these, sometimes we have this symmetry along, mirror symmetry along these two, both of the both perpendicular axes. Sometimes we have mirror symmetry along this one axis, and yeah, so this circle has curvatures -2 for the external, 3, 6 and 7 marked in white. Okay, so there are no threefold rotational symmetry with integers. No, that's not possible. So this circle, which has rotational symmetry, has a curvature of minus 0.928, yeah, the external one, and yeah, that's it. So this is just one fuzzy thing, pseudo threefold symmetry with integers, getting as close as possible. It's okay. So minus 15, 32, 32 and 33, so it gives pseudo threefold. I mean, what's good, what's good of that? Maybe something, but essentially that's all. This is the highest symmetry that this Apollonian packing can generate. Okay, so now we come to the residue modulo property. What is residue modulo? I mean, modulo n is, you divide any number with something, the remainder is called the residue. So as we have seen in the circle generated with the initial curvatures -1, 2, 2 and 3, so these are the curvatures written, and always if you see that if you divide any like ad infinitum, if you just um, divide the curvatures with 3, you'll see that 3n plus 1 type, which means let's say meaning 7, meaning 11, so not, sorry about that, 10, yeah, so these are not allowed. So the only allowed type are 3n and 3n plus 2. So it divide any number, either like with divide by 3, either the remainder will be 0 or 2, and therefore this has been done with two color scheme. There is no need of third color because 1 is never a remainder. Okay, so remainder 2, 23, remainder 2, yup, this one, 14, yeah, 3, 6, 14, 3, 6, 14. So remainder is 2 and remainders are 0, colored in brown, and this is colored in blue, of course, remainder 2. Divide by 5, you will get all the residues, 0, 1, 2, 3, 4. Divide by 5 anything, this divide, yeah, remainder is 1, okay, 23, remainder is 3, okay, having 2 remainder, anything, should be something, yeah, 27, yeah, having remainder 2, divide by 5, okay, anything having remainder 4, yeah, 14, yeah, so 0, 1, 2, 3, 4. Alright, similarly, this is this is one packing with integer initial curvatures, therefore all the curvatures are integers, and if you divide any one of them by 4, it's either the remainder is 1 or 0, yeah, that's it, either 1 or 0. anyone, choose any number. There is choose any number, divide it by 4. Either the remainder will be 0 or 1. So either it completely divides or the remainder is 1, and nothing like remainder 2, nothing like remainder 3, nothing like that. And so if you want to dive more into the properties, please refer to Elena Fuchs. She has some incredible literature on this topic, on the intersection of number theory in and in in Apollonian packings. Okay, here we are just talking about Apollonian network. Simply just connect the nodes, the adjacent nodes that just connect the adjacent nodes as we keep on generating smaller and smaller circles, and just connect the nodes. That's what we call Apollonian network. The property is we need 4 colors so that no two adjacent nodes are. It's pretty much common. This is the 4 color theorem in computer science. People know it very well. And yeah, the map of the world in 4 colors so that no two adjacent countries share the same color. So essentially nodes have been colored, keeping in mind that no two adjacent nodes have the same color. And if one fixes the color of the outer nodes, there is only one way to color the internal nodes such that no two adjacent nodes have the same color. So here, okay, so green, blue and yellow, we are pretty much fixed with pink, and the next will be like it has these neighbors blue and yellow, next will be green. So it is by default, it's just fixed. If you change the external, I mean, instead of green you pick maybe pink for an external vertex, well it just again fixes the internal color of the internal nodes. So essentially 4 colors. So out of 4 colors you can choose like this: 4 times 3 times 2 is 24, and divide by 3 for the symmetry. So essentially you have these 8 ways you can, yeah, color the external vertices, so that, and like 8 unique ways, let's say. The Apollonian network is Hamiltonian, meaning, well, it's named after William Rowan Hamilton, genius mathematician, contributed pretty much to everything from abstract algebra to mechanics, was Irish, and rumors say that he was drunk. Anyway, so uh, essentially this is a graph that touches all the nodes without intersecting. Pretty much this is like we used to play with in childhood. Maybe we used to play like this. People used random vertices, and then one had to uh, like cover all the vertices without basically repeating the same line, same edge, let's say, over and over again. So yeah, so this cycle exists. So this is Hamiltonian, and for any further diving deep, you can refer to this article. All right. Okay, so we see various types of configurations of the close packed circles. So essentially what we are going to say is that this configuration and this configuration are identical. Well, it's just a Mobius transform. The Mobius transform is defined by just by it is defined by the by AZ plus B upon CZ plus D, yeah, and AD minus BC not equal to 0, and where A, B, C and D are complex numbers, need not be real numbers necessarily. So the property is conformal, meaning that which preserves form. So essentially it preserves angles between intersecting curves. So this is basically the grid lines in rectangular system, the blue one, and it has been transformed to using this transform 1 upon z. So essentially A is 0, B is 1, C is 1 and D is 0, yeah. So this gives the transformation, which essentially if you see that at 0 comma 0 there is a discontinuity, it's undefined, but these circles, so it basically transforms to circles. We'll see how in the following slides. And they cut at like orthogonal grid points 90 degree to each other. They become circles and they cut at 90 degree to each other. So that's how they preserve angles of shapes in this mapping, let's say. Okay. Oops. Yeah. All right. Sorry about that. So here we see that the circles have been transformed under this transform where A, B, C and D values are given. And okay, so these gray shaded circles are the original circles and the blue and the red are the transform circles, which are which is a product of the following transformation. And after that, here we keep every other parameter same and we vary A. So as we vary A, we see that these circles transform, but the angles at which the circles intersect remains the same throughout. Similarly here, okay, maybe the greater circle can shrink. I mean the smaller circle can inflate, but what the transformation essentially preserves is the angle between the two circles. Once again, so here we vary C, keeping all other parameters same, and here it is. So essentially here we have just shown the transform using 2 by z, and yeah, so this line is, well, x equal to 2, yeah, so x equal to 2 gets transformed to the inner, okay, yeah, so x equal to 2 gets transformed to this intermediate one. As you move further away, x equal to 4, this transform into this inner circle, x equal to 1. Okay, this circle similarly about y, I believe this is y equal to 2, yeah, and so on. So we wanted to show that these two configurations are equivalent, and they are through Mobius transform. So this circle, this red one, turns into, keeping like through this it just So basically the infinite line is closing to a circle. So this infinite line keeping the pole at, so essentially this circle, this transform is exactly what I have shown here, mapped here. It's essentially minus 1 by z minus 1. So the y equal to 0 line extends to infinity in either directions, and through this transform it as if it coils up into a circle. Finally, we are talking about the Minkowski dimension in the initial part of the video. Now we will define, we'll see the Minkowski dimension is just another way of defining. So the problem is that in this kind of artificially generated curve, where this one line segment, it just like it just is one third of it becomes four segments, like it turns into four segments of one third of its length, and so on iteratively. So we know the direction how it is going. But for Apollonian gasket, oops, 2 2, and it's not, essentially the space is not uniformly shrinking. So 3 2 2 3 2 2. So these purple are what we get in the second iteration. So how many like gaps in the circle in the this one, like this one, this one, this one, and this one. So 6 6 3 and 15 are what we get in the next step. After this step, the circles what we get has been marked in yellow. So essentially see in the like we find 6 in the next step, and we find 6 in the previous step as well. So this decrease is pretty much very not so straightforward. So therefore we have a different way of, yeah, different way of defining dimension. And okay, so it's after Felix Hausdorff. What it says is that take circles of limiting of diameter limiting in the limiting case tends to 0, which cover this perimeter in this fashion, not this fashion. That is why we use the infimum term, right? So infimum, which means like of course you are not covering with overlapping circles, so non-overlapping circles, because like this is very stupid. So so we cover by non-overlapping circles, and yes, so the S will give the, so what power of the diameter, if we sum what power of the diameter, it covers the like diameter of the circles. Okay, see these are circles, and in the limiting case tends to 0, and what power of the diameter of the circles will cover this entire perimeter. So sum sum of what power of the diameters will cover the entire perimeter, right? Okay, so diameter to the power 1. Hello, that's infinity. We have earlier shown that the perimeter of a Koch snowflake is infinity. So no, we cannot cover this perimeter with diameter power 1. Let's try diameter power 2. Diameter power 2 or radius power 2, that's area. So hello, we measured the perimeter in units of area. That's absurd. I mean, in terms of area, the length, no, it's zero. It's zero. It's the area is zero. The area of this boundary of this cos snowflake, the area is zero. Very simple. Now the idea is to find, or pretty much from logic it it can be sensed that there is some, so when s transitions from 1 to 2, there is some s in which there is a jump from infinity to 0. Our Hausdorff dimension is that very s. So the there are pretty much works related to this finding out Hausdorff dimension, the very highest level, and the it started from this Boyd, who gave this approximation that the limit lower bound and upper bound, and this has been computed using numerical and computational techniques. Of course, there is no closed form solution as of date. So we see this paper by Thomas and Thor, where this dimension had been calculated pretty much accurate to 8 decimal places. And I would like to mention the name of Deepak Dhar, Professor Deepak Dhar. He is the first Indian to get the Boltzmann medal in 2022. And yeah, I mean, this video was kind of a motivation from there. And he worked on this Hausdorff dimension of the, yeah, great. I mean, he is attached to the ICTS, that is the International Center for Theoretical, yeah, Sciences in Bangalore, and great man. So yeah, it's pretty nice to have getting motivated. And this video is, well, yeah, it's just is a remembrance of these Professor Dhor's like great work in the in this area of self similar and fractal geometry. Because yeah, it's Boltzmann medal, it's after Boltzmann, it's the highest honor of statistical physics. Vytnova and Wormell, so they have calculated the Hausdorff dimension till 130 decimal places in 2025, and they have placed their code open source. I have placed the GitHub link, and it was it's just great. I will try to put the link in the description box of the YouTube video of Vytnova and Wormell, and yeah, it's very inspiring. It's very inspiring indeed. At the end, we come to the just another inspiration. This book I would like to recommend. So pretty much in architectures and theology, in all religions, in in the Islamic architecture, in the Buddhist theology, Hindu theology, and pretty much everywhere we find this exquisite geometry. And this book is not it says like Indra's Pearls. So basically Felix Klein was from the Göttingen University, and he was not just a good researcher, he was also a good educator. And it was his dream to just he saw these figures in his dreams, like exquisite figures. And it was, and these the authors David, Caroline, and Wright, they claim that it wanted to fulfill Klein's dream, in the sense, in the era of computer graphics, when it is possible to basically visualize uh, things. And so this is Indra. They well, let me very clear. This is not a religious book. This is yeah, this is serious mathematics book, and with a light-hearted touch, of course. So this is from Buddhist philosophy. So it's Indra is there, in is the king of god, is in Hindu theology, in Buddhist theology. But this as the authors demand, as the authors want to say, that they have like got the motivation from Buddhist philosophical theological writings about Indra's pearls and nets and ornaments, which are very very exquisite and just very wonderful. And and psychedelic art since antiquity. I mean, we have been very privileged to have these computer graphics in this, and to visualize which was Klein's dream, sort of, because it needs, well, it needs computational power, because certain simulations have to be run for long. And also the book Fractals in Probability Analysis by Christopher Bishop and Yuval Perez is also a very very nice book. And so hope you have enjoyed the video, and just leave all your um, questions and criticisms, and point out pretty much anything, mistakes and points of improvement, and uh, everything, whatever you feel. And thanks and cheers, and we'll see soon when we come back with the next video. Thanks everyone.